This is Professor Rudy, and this video is on how to use the Polyfit and Polyval functions for polynomial curve fitting. In this video, I'm going to go through 3 different examples of different types of fitting that you can do. The first one that I'd like to do is doing a linear fit, so fitting a line to a set of data. This example, I've already pre-worked this, so I'm just going to walk you through it. I'm going to start by generating the data. Now, typically, you're not going to do this step. This is usually you've recorded some data or you have some measurement that you're working with. So this is a step that you're typically not doing, but this is going to be the data that we're pretending we got this from some measurement source. So what I'm going to do is I'm creating a simple time vector from 1 to 20 in 1 second increments. And then I'm creating a line with that. So here I've chosen a slope of 0.4, an intercept of 1. And here's the key, is I'm going to add some noise onto this signal. I'm going to use the random normal function in MATLAB to generate some random noise to kind of mimic a real sensor measurement. So what happens when we do this, I'm just going to run this block of code right here. I generate that data. Now it's following a line, but it's got some variations in there due to that noise that I added in there. And this is probably similar to what you might see from some measurement. When we look at this, we see or we think, based on theory, that this has a linear trend, and we want to figure out from this data what the slope and intercept of that line are. So we're pretending at this point that we don't know what that slope and intercept are from this definition, because normally that'll come from a measurement. So the next thing that we want to do then is use the Polyfit command to fit a line to the data. So MATLAB already has a function that can do what's called a regression analysis in order to find what it thinks is the best fit to that line. This Polyfit command, let's even go ahead and do help Polyfit and take a look. This Polyfit command will fit a polynomial to the data, and it's going to do that by taking in inputs of x and y, so that's your data pairs, an xy data set, and then n here is using defining the degree of the polynomial that you want to use for your fit. So in this case, we're going to use 1, that's defining a first order polynomial or a line. And then if we send in our data into the command, so our time and our y value, for a first order fit, we will get out a polynomial. So when I run this section, we get this result here. The way MATLAB defines polynomials is as a vector of coefficients. So this polynomial here is like this value is the slope. So this times t plus this is our line. And we can see if we look at and cheat a little bit and look at what we put in, that slope is pretty close to 0.4 and that intercept is pretty close to 1. So this is doing a reasonable job on the fit, but it's always a good idea to look at your fit visually and see how it looks, because if we didn't know what those values were, we wouldn't really have a good way to tell just from these if it looks correct or not. So what we want to do is we want to plot that fit with the data. And we can do that using the polyval command. This is a function that works with Polyfit, because this will take as an argument here a polynomial. So you can use polynomials as long as you're following that right format. So you have this slope and intercept for a line, but in general it starts with the highest powers of the polynomial and then goes down until you hit the constant at the end. So using vectors of that form defining a polynomial, and then you give it the time values that you want to evaluate at, so you need to pass in your independent variable. Then what you will get is the corresponding dependent variable, the y value for the fit. So here then we have t and y, which is our raw data, and then t and y fit is now our fitted data. So I'm going to plot this now, run this section. And this is what we get. We have a circles marking the data as we have from our measurement, and then the red line is showing the fit. So when we see something like this, this is looking like that's a pretty good fit to the data. But we always want to do this visual check to see what's going on. And then once we do this check, we can go back and we can use these values for whatever it is that we're interested in. So perhaps the slope of this line was an important value that we were trying to calculate from our data. Maybe we were trying to generate a calibration function for this data set. But that's how to do linear curve fit. For my second example, we're going to do the same exact thing, except this time we're going to do this for a second order polynomial or parabola. So it's the same idea here, and I'm going to go through one section at a time. Same time vector, except now I have a second order. I've got a t squared term, a t term, and a constant term, and I'm still adding some noise on here. And so let's just take a look at that data. So this is what we're looking at for our data. So we could tell from looking at this, this doesn't really look linear, so we probably don't want to fit a line to that. So this is where, and we might not know this at the time, but if we wanted to fit a second order polynomial to this, this is how we do that. So that was generating the data. We still use the Polyfit command, and we still do our fit, but now all we need to do is change n from 1 to 2. And by making that 2, now we're going to fit a second order polynomial, and it's the same command. So if we run that section, we get this polynomial out here. And what this is telling us is, again, the coefficients of the polynomial, but now they're starting with the t squared, then the t, and then the constant term. And so if we cheat, look back up here, well, that first term that is close to the 0.2 that we put in, this minus 2 is pretty close to this, and this minus 4 is pretty close to that. So based on those values, I would guess that we have a pretty good fit. But we also want to take a look at that visually. So again, we can use this polyval command, and there's no difference here. We're still just sending in that polynomial. Whatever we found from our fit, we put that in here, get our fitted y values, and then here we're just plotting. So I'm going to run that, and we can take a look. So this is showing us what the data, the blue circles, and then the fit, red line, look like. So again, here we see that based on these measurements, that's what we expect the quadratic relationship to be. So then we can use these values for whatever we're looking to find. For the last example, I want to talk about an exponential function. So exponential functions are not a polynomial, but that doesn't mean we can't use these existing tools to do the fit. Because what happens is if you take a logarithm of the exponential, you get a line. So let's go through this. It's the same format, except now we've got this exponential. We've got some scale here and then some factor affecting the rate of that exponential, adding on some random noise here. Let's take a look. So this is what this data set looks like, and we want to do a fit to this, and we're assuming that this is an exponential. So when we go to do our fit for this one, and we go to do our polyfit, we're going to use n equals 1. We're going to do a linear fit on the data, and if we're assuming we have some form like this, like a e to the rt, all we need to do then is in our polyfit command, we still use time, but for our y data here, we take the logarithm. Now log in MATLAB is the function for natural logarithm, and if we do that, we should end up with a linear function of time. So when we do this with a first order fit, what'll come out then is we can get the values of r and a by doing this. R is just going to be the slope of the line. So here it's this rate inside the exponential, but when we take that logarithm, that becomes the slope, and then a, that scale we can get, but we need to take an exponential to essentially undo that logarithm and get that value. So let's go ahead and run that, and now we get these two values here. We have r as 0.2361 and a as 0.6. So if we just peek back up here, well, this was our a value, 0.5, we're getting 0.6, so that's not perfect, but it's close, and 1/4 here is like 0.25, that's pretty close to that r value, and the reason those are different, and the reason all these values are different, is because this random noise is messing with the fit. And that's why when you're doing a curve fitting, you're not necessarily getting a perfect result. You're getting your best guess as to what the function is based on the measurements that you have. And the more measurements that you have, the better of a fit you'll be able to get, the better guess. So just to finish this out, if we run this and get our fit, we can take a look. And here we see that based on the exponential function, using the polyfit, using linear curve fitting techniques, we can actually fit this exponential with a reasonable result. So these are the techniques that you can use to fit curves using the polyfit command. Now keep in mind, so we did first order, second order, and then exponentials using a first order fit. But you could do this with third order polynomials, fifth order, 10th order polynomials, depending on what function you're working with. So it's the same technique, it just changes your coefficients in your polynomial vector.